get going. Okay, can you guys remind me in here how far we got on the review sheet? Did we get that? Did we do A, the slope field? Oh, very nice. Okay, so to recap, full screen. But we were okay on coming up with the slope field ourselves at the 9 indicated points. Okay. So just remember when it tells you, to draw the slope field at 12 indicated points, when you're done, just do a quick check that you did the right number of them. Because it's sometimes, especially in the AP exam, they'll make the points on the axis and you don't see them. And then you lose points. So. Okay, so we did that one. Then B, we separated, we integrated, we actually solved it. This was a fun one. Did we get all the way to this solution? Yeah. Okay. So we didn't do the limit part, did we? Okay, so that's what I want to take from. Is that right? Okay. So we got our solution by separating, integrating. We solved for C, and it was a little weird, but we actually enjoyed it. We said at the end, we all agreed that that was good. So then, for the next part, C, yeah, remember, we took a vote. So this is 6C, we're asked to find the limit as x approaches infinity of our solution, which was negative e to the 1 half minus 1 over x, and then plus 1. Now, we'll see. Wow, look how I did the limit there. That looks a little lumpy. Okay, so now, when you go to find a limit as x approaches infinity, define where the x is, because that's the part it's going to affect. So if x is approaching infinity, that's down here, this denominator is approaching infinity. Now, then the next thing you want to do is say, okay, so if the denominator is approaching infinity, what about the whole fraction? 1 over. Now, I want to make sure you guys understand, if you have a fraction, the numerator is 1, or any number that's not changing. And the denominator is just getting larger and larger and larger. It's going off. The denominator is going to infinity. What value is the numerator approaching? 0. See, that's what you want to do. See, okay, so if x is approaching infinity, the whole fraction is approaching 0. You just did all the limits you have to do, because when you see how it, how it affects the parts with an x in it, that's what it's going to do. So the limit is what's left. Nothing else is going to be affected by what x does. Nothing else has an x in it. So what we have is then negative e to the 1 half minus 0, right? As this instead is going to 0, plus 1. Oh, that's important. I'm going to, if it was to the negative infinity, no, that would be the same thing, because it's 1 over e to infinity. Yep. Okay, because, so x is approaching infinity, that's the denominator. The numerator is 1, okay? So you got to think about the whole fraction. What's going on with that? So if the numerator is 1 and the denominator, I stopped because I got tired and I ran out of leash. But if I just kept going, think about a fraction, first 1/10, that's pretty small. 1/100th, that's even smaller. 1 over 1,000, 0.001. And if you just kept going, you're just going to get closer and closer to 0. That's why anytime you have the limit of a fraction where the denominator is going to infinity, it's always going to be 0. Okay, so this is our answer. I'm just not going to leave it minus 0, so our answer is negative e to the half plus 1. That's our limit. Now that's the same thing as saying, you can leave it like that, but 1 minus rad e. But the other one was fine. Can I just do one extra little problem with this for you? I just want to show you something. Suppose I asked you for the limit. With these limits involving infinity, never leave a negative exponent. Let's say we wanted the limit as t approaches infinity of e to the negative t plus 100. What I want you to do before you just like think about t going to infinity, first of all, rewrite it without the negative exponent, because they will mess you up with limits approaching infinity. So how are we going to rewrite the e to the negative t? 1 over e to the t, and then this is just plus 100. Now we're ready to get the limit. If t is approaching infinity, what's going on with the denominator? Well, just the denominator, e to the infinity, it's going to infinity, but like what you were thinking here, the whole fraction, 1 over a number that's going to infinity, is approaching 0. So we get 0 plus 100, which is 0, which is 100. Whoops. Woo. Okay. Now, if that was not a negative t, but a positive t, what do you think the limit would be? E to the infinity plus 100. Infinity. So with infinity, it's really important. If that infinity is in the numerator, that's infinity. If the infinity is in the denominator, that's 0. Well, when you're talking about with exponents, yeah. That's why never leave a negative exponent when you have to take a limit involving infinity. Rewrite it first, and then you'll have one of those cases. But then your answer would just be infinity, though. You wouldn't write infinity plus 100. Okay? Just infinity. Yeah, bigger. Okay, so, all right, the next one, was that when the slope's going to be negative? Yeah. Get rid of this stuff. Get all this stuff. Okay. The derivative is the slope, and they're asking you when the slopes are going to be negative. So your derivative is either going to be a product or a quotient. That's how these differential equations are. They're always products or quotients, or else you can separate them. So this one's a quotient, and we know a quotient is going to be negative when you have a positive and a negative. It's just that the numerator can never be negative. So it would have to be positive, and the numerator would have to be negative. So the only way that this derivative, this slope, could be negative is when the denominator is positive and the numerator is negative. Does that make sense? Okay, because it's a fraction, it's negative. Normally I would say or when the denominator is negative, but that can't be. That'll never be negative. So that's why I don't consider that. So it will be any point x, y such that the numerator is negative. For y minus 1 to be negative, less than 0, that would mean that y would have to be less than 1. I just added 1 to both sides, the inequality. And for x squared to be positive, I know you think anything squared is positive. You just have to remember the one number that if you square it, that won't be positive is 0. So for x squared to be positive, x just can't be 0. So the slope will be negative at any point xy as long as the y coordinate is less than 1 and the x coordinate is not 0. You can't just list the points where it would be negative because they only show you a few points on there. You have to remember there are all these different numbers other than integers. And you don't want to just think about integers when you're thinking about coordinates and points. You got to remember there are all those other numbers. How's that one? Was that one boring? Yeah. Well, it'll get good now. Is the next one the second derivative? Well, because for a fraction to be negative, it could either be a negative over a positive or a positive over a negative. Okay? Right? For a quotient or so, but the thing is there's no way that x squared is going to be negative. So we know the only way this fraction, this slope is going to be negative if the top's negative and the bottom's positive. All right, so the next one's the second derivative. Somebody's looking at me. Hi. She came here for us, so we feel honored. Oh, wait, we got to get you a... oh, there's one back there. Is there paper on there? Are there solutions on that desk? Okay. Oh, here it is. Okay. So, guys, the next question that you see a lot with the differential equations, it says, what's the second derivative? You're always given the first derivative in a differential equation problem. How do you go from the first derivative to the second derivative? Take the derivative, obeying all the rules. So, you're given the first derivative, dy dx equals y minus 1 over x squared. You did it right, good. Second derivative, if you got this wrong, guys, the answer turns out to be 3/16 if you have in your solution. You probably didn't get the right d high, because we had to use quotient rule. So we did low d high. The derivative of the numerator with respect to x is dy dx, not just 1. So check if you got that part wrong. But then the rest is okay. Less high, d low, all over the denominator squared. Now, I know on my answer key, I cleaned it all up and made it so pretty and factored out a y minus 1. You don't have to do that. You could just plug in the coordinates, because we want to get the second derivative at the point 2, 0. You could just plug it in right away. You don't have to clean anything up first. The one thing you're going to have to do, though, is realize that dy dx, the d high, is y minus 1 over x squared. So you got to put that in. That's why I have here 0 minus 1 over 2 squares. And then you just put in the 2 for the x and the 0 for the y, and you're good to go. And if you do it all right, you find out that the second derivative at the point 2, 0 is 3/16. Yes. Yep. You want right now? Corner my desk. Any questions on this one? Anyone get this one right? A few? All right, kind of. Almost? Okay. You see where the mistake is? All right, we'll forgive that. We will forgive that. All right, we're moving on then? Sure. Okay, so the next part, again, we have the derivative. We're given the differential equation, and they want us to write the equation of the tangent line at the point 2, 0. Write the equation of the tangent line to f at the point 2, 0. Well, this part, I'm just going to go do something. That part you want to be so good at. If anyone asks you to write the equation of a tangent line to a function f at a particular point, this part should be automatic by now. If not, get it down. To get y1, you plug the given x value into the function. To get the slope, you plug the given x value into the derivative. Yeah, what'd you get? All right, so f of 2, what's that? That's just 0, right? That's what they gave us. The only thing you have to get is the derivative. They give you the derivative. This is a differential equation problem. So the only thing that you really have to do, to get this slope, you just got to take the derivative, which is y minus 1 over x squared, and plug in the 2 for the x and the 0 for the y. And you plug and you chug and get negative 1/4. That goes here. So you got the equation, the tangent line, and then in the next part they say use it to approximate f of 2.1. What do you do for that? Yeah, you plug the 2.1 into the x of your tangent line. Psh, easy breezy. Easy. Yep. Oh, sorry. That would be a bad approximation, because if you drew the tangent line when x was 2, and you went so far away, that tangent line and the graph they're not going to be near each other anymore, so that would be bad. That's correct. 0.025. Okay. So, writing the equation of a tangent line. Now, there's something I didn't put on this paper that I'm just dying to know. We got our approximation. The part before, we found the second derivative at 2, 0 was positive 3/16. Yeah, would that make this an under approximation or over approximation? Under. All right. So here's the thing. Remember we found that where we drew the tangent line at that point, 2, 0, we got the second derivative was positive. It was positive 3/16, which tells us that our function's concave up there. So when we use the tangent line drawn there, oops, I missed it. Oh well. To approximate f of 2.1, we're getting the y on the tangent line at 2.1. So it would be less, it would be an under approximation. So this value, this approximation we got is less than the actual. The actual value is going to be greater than that. I should have thrown that on there. That would have been a good one. Yeah. Maybe it's still good. Alright. What's next? But that was the end of this problem, right? How about the translation one? Did you just translate it? You didn't have to do anything with it. The next one, I hope you tried it. I didn't check because, you know. Oh, I didn't even write it on here because I figured you just do that. Yeah, I'm not even going to insert a page. So for that one, it said the rate of change of the radius is directly proportional to the square root of the volume. Did you get that? Directly proportional to. How do we translate that? Directly proportional to k times. Oh yeah, when they say the rate of change of the radius, that's dr dt. Yes. Directly proportional to will just be k times whatever. Okay. All right. So for 8, it was one of these Newton's law of cooling or heating, which I think this was a cooling because it's the same thing. So we can use for these cooling or heating problems this Newton's law here. And do you remember what capital T stood for? Temperature. What about little t? So the thing is, they tell you it takes 20 minutes for the temperature to go from 210 to 120. They tell you that so you can figure out K. So this 70 is just the room temperature, okay? But this is your original temperature, and this is what it cools to after 20 minutes. And then they want you to figure out the temperature after 1 hour. Well, once you figure out what K is with this, you just got to plug 60 into time. You can't start switching units. You have to stick with the minutes. So you use this equation here to solve for K. Now, I just did arrow magic. Does anyone need me to go over how to solve for K here? It's just a constant, and it's just like a rate of change. Like it could be just a small decimal or something. Okay, it's just yeah. You could have also done that. Yeah, correct. Yeah, that was a good question. So if you just made the 20 minutes 1/3, you could have kept the 1 for the other time, but your answer would have been in hours. Does anyone want me to go over this one, or do you get this one? So you get the K from the, and then you can figure out what T is when the time is 60. It's always about getting that value K first. You got to get the K first. All right, I don't want to bore you with it if you know it, because you guys seem like it. All right, 9 is another one of these, well, I should say another one. It's the law, it's exponential change. You're allowed to use y equals y0 e to the kt. Now, in this one, the original population, the y0 was 30,000. And 10 years later, so when t is 10, the population is 39,000. Why do they tell you that? Define k. So what's the first thing you would have to do to get k here after you plug those values in? Yeah, you divide each side by 30,000, right? And then you could ln and divide by 10, and you'd get, it's the ln of whatever I said there, 13 tenths. Oh, because I divided by 3 over 10. Once you have k, you can find out what the population is when t is 20. You just put 20 in for the time. You'll know what k is, and you just multiply this all out. You pop that all in your calculator. try it, get it right, or what's that? No, I just don't know what to get rid of. What's your favorite one? You love decay? Oh, I'm taking off for that. I'm taking off. What? That is a great idea. It's not going to happen, but it's a great idea. Giving you any kind of option in life. All right. So anyway, we've got this population. This is the second part of this one. You started out with 30,000. We figure out at this point what K is. I forgot what it was. ln of 13 tenths over 10, I believe. Well, we got the first part of this. Um, we found out what K is, and then we could plug in 20 and get the population after 20 years. So what? No, that was 9A. I didn't write down the answer. I didn't feel like putting that into the calculator. You have it there, right? Yeah, that sounds good. Okay. But then the second part of that says, well, how long does it take the population to double? There are several ways you can find out how long it takes the population to double. If I know kids, probably the easiest way for you would be to put in what and solve for what? What would be the easiest way? 60,000 and solve for T, right? But can I just show you something? If you put in 60,000 here, which is a nice direct way of doing it, think about what your very next step is going to be. To divide, and what will you get if you put in the right value for y? 2, right? So if you do this and you divide and you have 2, and then you take the ln of both sides, you'll have the ln of 2. Yeah, that's what I'm showing you. So you can either just know the doubling formula or go through the motions if it makes you feel better. And that's equal to k times t. So the time it takes for a quantity to double is just the ln of 2 over k. So you can put in the, or you could put in 1 here and 2 here, or 3 and 6, or 10 and 20, or 15 and 30. It doesn't matter as long as you make this double, because that very next step you're going to divide, you're going to have a 2. So the doubling time will always be the ln of 2 over k. Ah. So either just plug in a number in for y that's double what you put in for y0, and it doesn't matter if they can, or just use this. Because if you just, even if I just put in 1 for how much I start, and then I put 2 here, okay, I'm always going to get for the time, it's always going to take the same amount of time to double with these functions. Nice? So maybe at home you want to try it all different ways. Alright, that was 9. Is 10 the one you hate? Yeah, I knew you would hate this one because we didn't really. Don't even. This is fun though. Given the half-life of carbon-14 is 5,700 years. So it takes 5,700 years to wind up with half what you started with. Yeah, see, this would be the easy way to get K. Just like all the other exponential growth or decay problems, you got to find K first, okay, before you can do anything else, before we can answer the question. Now, if they're telling us this is the time it takes for the quantity to half, you can either know the formula for half-life, or now you have y equals y0 e to the kt. If you don't want to memorize a formula, If they've given you the time that it takes for the quantity to halve, where am I going to put that time? Into t, right? I know, but sometimes, we get a little foggy. It doesn't matter what you put in here and here, as long as y is half of y0. Okay? So, what do you want to put in for how much you start with? You want to put in 1 and then you're going to have a fraction, a decimal here? You can. It's fine. I think 2 would be good, right? So, if you start with 2 grams or whatever it is, after 5,700 years, how much are you going to have? 1. Right? You could put in a 4 and a 2 or a 6 and a 3, because that very next step when you divide, you can divide by 2. What are you going to have on this side? You're going to have a half, right? E to 5,700. K, and to get K, you're going to ln it. Don't E the E. Okay. So when you ln it, now, if you're fine walking around with the ln of a fraction, fine. It's fine, but it's awkward, right? Yeah, thinking an ln of a decimal. Can't we be a little more sophisticated than that? Ln of 1 minus ln of 2. Ln of a fraction, log of a fraction. Log of the numerator minus the ln of the denominator. Why would you do that? It looks so much worse. Because what's the ln of 1? 0. So, you don't have to get K. But I'm just saying, you can keep it the ln of 0.5. Right? I don't want to discourage you from that. There's nothing wrong with it. It just looks nice. So the ln of 2 equals 5,700 K. And we want to solve for K, right? So K will be negative ln of 2 over 5,700. Now, you don't have to do all this work I just did if you know the formula for half-life. The time it takes for quantity to halve, who knows it? Negative ln of 2 over K. So if you cross multiply and solve for K, K is always negative ln of 2 over the half-life. See that? If you put this over 1, so so the half-life is negative ln of 2 over K. If you cross multiplied and divide by the half-life, time takes to halve. To get K, the really easy way, it's always negative ln of 2 over the half-life. Or just plug in the 2 and the 1. Do it that way to get K. But once you know K, now you can answer the question. Are we ready to answer the question? So let's just see. So now we know K equals negative ln of 2 over 5,700. Nice. Y equals y0 e to the kt. And we know what the K is. The question is, how old is the sample? So what are we looking for? T. Now here's the fun part. It doesn't give you actual values. It says in which 90% has decayed. Yeah, anytime you're just given percents instead of real values, make your starting value 100 since it doesn't matter. Okay? Because it's always... So, but here's the thing. In this formula, y has to be how much you have, not how much is gone. So if you started out with 100 and 90% decayed, how much do you have left? 10%, right? And so 10% of 100 is 10. Then I have my E, I have the K, negative ln of 2 over 5,700, T. Then you can solve for T. Find out how old the sample is. That's a lot of years. What is the first step, though, in solving this for T? Oh, I gotta get to it. Divide by 100, right? And then ln, and multiply by the circle. That's good. But these are kind of fun because there's no cow. Oh, maybe that's why it's not fun, because there's no cow. I don't know. Okay, I wanted to talk about this one. This is the last one, right? This one I like. I think this one I based it on an old AP problem where they did this. And if you couldn't translate that into symbols, into a differential equation, that would have been pretty bad. You wouldn't have had to start. That's why it's so important. It says you got a population that's increasing at a rate, so dp that is directly proportional to k times 2000 minus p. Now, they use p of t, that's the function notation. I like to just use p until the end, and then I make it look all fancy by putting it in like function notation p of t. But this is what they're giving us to begin with. Instead of just giving this, which would have been nice, they made us translate that. But then it's easy after this. Okay. First step is we got to find p of t. We got to solve this differential equation. What do we do? Separate and integrate. Now, it says in terms of t and k, that means we don't have to find k yet. We can just leave the k. All right, when we separate, I'm just going to go to a blank page. I need room. When we separate this, no, I'm saving it. When you guys are blue worthy, I'll use the blue. Okay. Actually, separate it correctly, and I'll switch to blue. Yeah. I'll separate first. So what's the dp going to be over? 2000 minus p. So you would bring that over to the other side by dividing. You always divide or multiply with these problems to move things around. And on the other side, we still have the k, right? And then what else? dt. So we separate the two variables. Population and time are your variables. Integrate. All right, I told you. Now, if you made a mistake in this, if your answer's not right, I think your mistake is coming right up here on the left. Why? We always just get ln. When we know that when you take the antiderivative of du over u, you get the ln of u. And it's always been working out that way. But this time, the numerator isn't quite the derivative of the denominator. It's missing a little something. Do you see that I would need a negative up here? No? What is the derivative of 2000 minus p? Minus 1, right? We would need? So we would need a negative 1. See, the other ones we've had, it's been like p minus 2000. So the derivative was 1. We didn't need anything up there. So you have to put a negative 1 on the outside. So, yeah, I can see messing this one up. So it's negative the ln of 2000 minus p. So that was the one little c thing here. The other side, you're integrating a constant k with respect to t. kt. Okay, now, we're so used to just getting ln that we can exponentiate right away. But this time, we got somebody who's in the way. Oh, I have to go back to the blue again. Yeah, you can't exponentiate until there's nothing in front of the ln. They got to be together. So I would multiply each side by negative 1. The ln of 2000 minus p equals, now remember, keep c simple. If we multiply each side by negative 1, I did that, great. I got to multiply kt by negative 1. But, am I going to call this negative c? No, just keep calling it plus c. Just keep things easy. Now we can exponentiate. E to this side equals e to this side. This side, when you exponentiate the ln of anything, that's just freed up. Do you remember what to do when you exponentiate and the plus c is up there? Bring it in front. Do I write c plus? No. Times. You don't have to do that. Okay. And now we do have to get c though, because they said give us what p equals in terms of k and t. So we do have to get c. They told us that the population is 50 when t is 0, right? When they said p of 0 equals 50. So we just plug in the 50 for the population. and the 0 for the t. So what do we get for C? 1950. What's that? We could. I don't, the moving over, you can, and then getting the C, they're like the same kind of level of importance. So now we know that C is 1950. You go up to the line above where you plugged in the numbers and plug in the value that you got for C here. So now we've got 2000 minus P equals 1950 e to the negative kt. So this is it. The only thing is I just have to get P by itself. So if you move, like if I add P and subtract, move things around, I get that P is equal to 2000 minus 1950 e to the negative kt. Now, this is my final answer. I just like to make it look fancy, so instead of just calling it P, I'm letting the world know it's a function of time. When we needed a negative to make it an ln, and we had to multiply each side by -1 first. Okay. No, that wasn't terrible. And actually, there's a cool part in this, because, well, the next part is easy because they say solve for k. So you put in the 1200 for the p and the 2 for the t. That you can do. But the part that I wanted to make sure that I mentioned, watch this. Then they say, what's the limit as t approaches infinity? Yeah, see that exponent's negative? So are you going to leave it looking like that? No. You're going to rewrite it as e, whatever you got. I'm just going to leave it k. T, and if t is approaching infinity, what are we going to get? 0 for the whole thing? No. So we'll get, this guy doesn't care what he's doing, but this is 0. Any number over infinity is going to 0. So it would just be 2000. I'm here after school if you didn't get enough. Oh yeah, you can have fun in your drama in the pit and staying here till late at night. Oh, blank reviews are here. Blank reviews. Here in the corner. Here in the corner. What's that? Oh, thanks.